In this video, we will see another very nice application of the first derivative, basically called linear approximation. So this application is motivated by a very natural observation, right? So if you are given a function, the function might be very, very hard to evaluate, right? And take lots of time and energy. And so we are given a function like this, right? Imagine this is a function which is very hard to evaluate, which is as that, right? We are given a point, let's call that A here, right? By our evaluation, you have a point in the curve, which is A f of A, right? Now you can see that you can sketch a tangent line. Let's use red. This is a tangent line to the curve, right? Tangent line, normally that's a linear equation, y equal to slope of times x plus something, right? And I can see that as x is very close to A, this red tangent line is kind of very close to the black function curve. But function value is very hard to evaluate. This tangent line equation is very easy, right? So we want to use our tangent line equation to approximate this very complicated curve. So that's the idea. So you can see that the very natural observation here, let's call this line equation to be L of x, the tangent line, right? So observation here is when x is close to A, then L of x is very close to f of x, right? So that's basically our very natural observation, right? Let's try to write down the line equation, try to figure out what's our line equation for the tangent line, right? So that's basically the idea behind linear approximation. So the tangent line equation, okay, this tangent line here is to the curve at the point A f of A, right? That should be y minus f of A equal to the slope is f prime of A, then x minus A, right? Rewrite it our basically y equal to f prime of A, x minus A plus f of A. So this is the tangent line equation, right? And so we give a new name. We call that Lx. So we write this as L of x equal to f prime of A here, x minus A plus f of A. So this is our tangent line equation in a different form. This is called the linear approximation of f at A, right? And also called the linearization of f at A, right? They are same thing. That's a very, very important formula. So based on our observation, when x is close to A, the function value of f at that x can be approximated by L of x, right? But this equation normally is much easier to evaluate, right? Let's try to do a quick example here. Example, we are given a function is f of x equal to root x. We are given a number a equal to 4. So our first part is we are looking for find the linearization of this function at this number, right? Now, how do we do that? You just need to figure out what is f of a, what is f prime of a, then you are done, right? So we know that f of 4 equal to root 4, which is 2. Now we want to get f prime of a. We know that f prime of x is 1/2 x to negative 1/2. So f prime of 4 is 1/2 times 1 over root 4. So this is 1 over 4, right? So that's all the numbers we need for the linearization. So our linearization of this function equal to f prime of linearization of this function at 4, right? F prime of 4, x minus 4 plus f of 4, right? So this is equal to 1 over 4 times x minus 4 plus 2, right? Okay, B here is why do we need this linearization, right? So what we want to do here is we want to use A here, use the linearization to estimate square root of 3.9498 and square root of 4.05, right? Okay, so let's try to do that. So so this square root of 3.98 is basically f of square 3.98. That's clear too, right? Because our function is root function. This number is very close to 4. So this can be approximated by L of 3.9498. This number is 1 over 4, 3.98 minus 4, then plus 2. If you try to evaluate that, this is basically 1.995. So that's a decent, that's a good approximation with decent accuracy, right? Now, if you want to approximate root 4.05, this for sure is f of 4.05 because f is our root function. So this can be approximated again here. You can see that 4.05 is very close to 4, right? This can be approximated by L of 4.05. So this is 1 over 4, 4.05 minus 4 plus 2. So this is basically 2.0125. So that's an example where we can find the linearization of function and also try to use it to approximate some number which is very close to A, right? Now let's see one more example. We want to use either linear approximation or linearization, same thing, right? We want to use them to use linear approximation and to estimate a number which is 8.06 to the power 2 over 3. Okay, look at this number here. Now you can see that when you change 8.06 to 8, you can calculate that, right? Just notice 8 to the power 2 over 3 is third root of 8, then square, which is 4, right? So, and also 8.06 is close to 8. So this suggests your the A in your linear approximation should be 8, right? So that's your position of X. So we can choose our function accordingly, right? So based on our observation, our A here should be 8. F of X should be X to the power 2/3, right? Different choice of A, you have different choice of the function, right? So from here, by our calculation, f of a should equal to 4, right? F prime of x is 2/3 x to negative 1/3. So f prime of 4, 8, equal to 2/3 times 1/3 root of 8. So this is 1/3. Now we are good, right? So the linearization of f at a equal to 8 is what? Is, let's use our standard notation, is equal to 1/3 x minus 8 then plus 4, right? So 8.06 to the power 2/3 is f of 8.06, which is about the L of 8.06 because this number is very close to 8. So this is 1/3, 8.06 minus 8 plus 4. So this is 4.02. So that's a good approximation of the number, which is 8.06 to the power 2/3.